Informally, a limit is a y value which a function approaches as x approaches some certain value. The notation for it is the limit as x approaches c of f of x equals L. That would mean that as x is approaching the number c, f of x is approaching some y value L. Find the limit of f of x as x approaches -4. As the x's are approaching -4 from the left and the right, what y value is this approaching? The y value that we're approaching is 1. And in this case, it just so happens that the limit is also equal to the value. So f of -4 is 1 because the point at -4 is -4, 1. The limit of f of x as x approaches -1, so we're looking from the left and the right as x approaches -1, what are the y values approaching? This is a y value, but it is not what we're approaching. The actual graph from the left and the right is approaching the y value of 4. Now f of -1 is the y value at -1, and that is 1. As we're approaching 2 from the left and the right, the y values are approaching 1. What is f of 2? F of 2 is undefined. There's actually no point where x is equal to 2 on this graph. The limit as x approaches 3 of f of x, 3 is a vertical asymptote, and as we're approaching 3, the left side is approaching -infinity, and the right side is approaching -infinity. Even though our limit does not exist, because -infinity is not a number, we write -infinity as the behavior of which the limit is headed toward. And f of 5, that would be the defined point at 5, so 2. The limit as we approach 5 from the left, that is -1. But as we approach 5 from the right, that is 2. Because the left side and the right side limits do not match up, if I were asked to find the limit as x approaches 5, not a one-sided limit, that would not exist because there is a jump or break in the graph. For continuity, informally, a function is continuous where it can be drawn without lifting a pencil. Roughly, continuous means connected. Formally, a function is continuous where its limit and its function value are the same, as in at x equals -4. In this course, we will work with 3 types of discontinuities: holes, which are removable, vertical asymptotes, which are non-removable, and jumps or breaks, which are also non-removable. List the x values of the discontinuities and classify their type of the function y equals f of x graphed above. All right, we have several discontinuities. A hole is a discontinuity, and so we have a hole at x equals -1. And that would be classified as a removable discontinuity because it is just a hole. We also have a discontinuity at x equals 2, another hole, removable discontinuity. Then we have a vertical asymptote at 3 and a jump or a break at 5. And those would be classified as non-removable. At x values where a function is continuous, limits can be found by direct substitution. This is a parabola which is continuous. All polynomials are continuous, so we can directly substitute 3 in for x. 3 times 3 squared plus 2. This function is not continuous for all x values. It has a hole at x equals -1, which would make that denominator 0. But that's not the value they're asking us to find the limit of. And the value they're asking us to find the limit of, this function is continuous at x equals 1. So we can just direct substitute. And that's our limit. For a piecewise function, a one-sided limit evaluation is often necessary. To find the limit of f of x as x approaches 1, we notice that for x is less than or equal to 1, we have a line, and for x is greater than 1, we have a parabola. So 1 is what I like to call our transitional value. If they're asking us for the limit as x approaches 1, and 1 is the transitional value, then we have to plug in 1 to both parts. We have to find the one-sided limits in order to determine if the limit exists. So the limit as x approaches 1 from the left of f of x is what happens when we plug in 1 into the first piece of the piecewise function. 4 minus x, so 4 minus 1. Then when we take the right side limit, even though 1 is not defined in the right side or the right piece of the function, we're still finding the limit, so what it is approaching. So we're still going to direct substitute for this one-sided limit. The left-hand limit is 3, the right-hand limit is 3, so the limit of f of x as x approaches 1 is 3. If these numbers do not match, if the one-sided limits do not match, then the limit does not exist. That would mean there's a break or jump in the graph. To find the limit as x approaches 1 of g of x, we're going to do the same thing. 1 is, yes, our transitional value. Half of the function is defined to the left of 1, and half of it is defined to the right of 1. So to find the limit as x approaches 1, I'm going to take the one-sided limits and then see if they match up. For x is less than 1, I'm going to use the first piece. And for x is greater than 1, or as we approach 1 from the right-hand side, I'm going to use the second piece. Those one-sided limits do not match up. Therefore, the limit would not exist because there is a jump or break in the graph. Now to find the limit as x approaches -1 of g of x, notice that -1 is not our transitional value, so we don't need to find one-sided limits. We just need to find which piece of the piecewise function -1 applies to. -1 is less than 1. So we're going to direct substitute -1 into the first piece of the piecewise function and therefore find this limit. And there's our limit. Another function requiring one-sided limit analysis is a step function called the greatest integer function, also known as the floor function. It either has these halfway brackets like L's or full-on brackets. It means that whatever is inside of those brackets, find the greatest integer less than or equal to the thing inside of those brackets, and that will be your result. So here you have the parent function, regular floor function. What is the limit of the floor function as x approaches 1/2? Which is right here. The y values are approaching 0. What about as x approaches 1? From the left, we approach 0, but from the right, we approach 1. Therefore, the limit does not exist. For 19 through 21, we have variations or transformations of the greatest integer function. So we're going to plug in numbers and evaluate what it's approaching. To find the limit as x approaches 3 from the right of this floor function, I'm going to plug in numbers that are to the right of 3, like 3, 3.1, and 3.2. 2 times 3 minus 1. So the greatest integer less than or equal to 5 is 5. 2 times 3.1, that would be 6.2 minus 1, so 5.2. The greatest integer less than or equal to 5.2 is 5. And this one will also equal 5, but we didn't really need to do 3.2. As we're approaching 3 from the right-hand side, we are getting 5. Now, if this 3 did not go to 5, our limit could still be 5. It could be asking for the one-sided limit at a jump, and that does exist. Let's try this one. This one's asking for as x is 1, so I'm going to plug in values to the left and right of 1. The greatest integer less than or equal to 1.9 is 1. The greatest integer less than or equal to 2 is 2. The greatest integer less than or equal to 2.1 is 2. From the left side, we're approaching 1, but from the right side, we're approaching 2, that means the limit does not exist. So the value at 1 is 2, but the limit does not exist because we're approaching two different values on either side. And let's try this one. All right, the greatest integer less than or equal to each of these is 1. So from the left and the right, we are both approaching 1. Therefore, the limit as x approaches 1 is 1.